Complete process of executing a regression model and a classification model. I'm trying to cover some algorithms here as well as some more concepts. So we have seen regression, binary class classification and multi-class classification. So today we are going to cover multi-label and multi-output, two more variants. So I'll explain what those two are, maybe after a brief recap of what we covered yesterday. So when you have the k nearest neighbors algorithm takes the training data, puts into memory. When you ask a new question, then it goes and tries to find out closest records to that particular data. And based on the output values of the closest records, the decision is made. Probability is calculated based on the output values of the closest records. So out of these three closest records, two were defaulted. Sorry, one was defaulted and two were not. So out of three, two were not defaulted. So most probably this guy is not going to default. So that's how the decision is made. But here the k need to be decided by us. Right? As a data scientist, we need to decide. So how to choose k is a big question. Okay, I'll show you, with a code example on how to choose k. So how do you know that I should be looking into 3 neighbors only or 5 neighbors only or 4 neighbors only? How will I know, right? That's a question. We'll answer that today. And how the distance is calculated, there are two metrics I have given, Euclidean distance and Manhattan. Either one can be used. Generally Euclidean is used. So how is it calculated? The question has got two attributes, right? The input, the training data also has got two input values, and the distance is calculated like this, right? Square root of first value x1 minus x1, x2 minus x2. I denoted this as p, right? And this as x. Okay, so I got it, but it looks like the bigger value is dominating, even though there is, if somebody is of 20 years of age who took loan and somebody is of 70 years of age and that guy also took loan, there is a 50 years difference. If there is a defaulted, not defaulted difference also, the 50 years is almost 50% of a human's age, right? So that's very significant. But when you square that value and add it to the additional whatever, right, it is like it is nullified. It's not even showing up here. So to make all features important while calculating the distance, we should be normalizing the data, right? Either divide by maximum or standard scaling or min max scaling, whatever scaling you want you can do. But the data, if the data is on similar scale, the distance metric is going to be perfect. When the distance metric is perfect, your decision is going to be correct. Okay, to make KNN algorithm work better, you should be doing scaling. Okay, feature scaling is important here also. We have seen feature scaling is important in gradient descent, right? Now here also we are seeing feature scaling is important, and again in SVM also we'll see feature scaling is important. Okay, in deep learning anyway it is all going to be gradient descent, so feature scaling is definitely important. So that's where I said feature scaling you need to understand. Okay, now let us see how to choose a k. Okay, I'll show you code example and then come back to this theory. So I have taken a multi-label classification problem to explain the k nearest neighbors algorithm. So KNN can handle multi-label classification also. Let us try to understand what is multi-label classification. Oh, give me one second. Forgotten to correct this. Now, if this multi-label and multi-output classification variants are easy to perform in deep learning. Okay, I'll show you how to do that there, but understand the concept here. So we have seen two kinds of classification, binary and multi-class, right? So binary, multi-class. Okay, in binary, we had n number of features and a y variable. Right? There are m number of records. Okay, and then each record is belonging to either 0 or 1, like that. This is binary. Okay, and multi-class, same m number of records, right? N, n can be different or same, or doesn't matter. So n number of features, right? The target variable is having multiple labels, right? 0, 5, 7, 9, right? We had seen 10 classification. You can have 100 classes also, 1000 classes also. Okay, so this is called as multi-class. Now multi-label. Okay, multi-label classification problem. So in the multi-label classification problem, the multi-label classification problem is a more generalization of binary class classification. So there will be x1, x2, and so on, xn, right? And then m number of rows, right? There will be y1, y2, and so on, yk, or y maybe r, some number. There will be multiple y values, multiple y features. Okay, maybe y3, y4 I'll put. Okay, 4. In this particular problem, right, I have taken emotions data set. In there we have 6 y variables, y5 and y6. Okay, so each y will have either 0 or 1. Each y is a binary class classification problem. Okay, this is multi-label. Okay, so far is it good? Any questions?
Not able to visualize the realistic case of multi-label, sir.
I'll show you. Multi-label, okay, sure, realistic case. But if the data is like this, right, then we call it as multi-label. Okay. How can we solve this problem? And how can we build a model for this? If you, with your current knowledge, can you build a model for this particular data set?
I think we need to take all the input once and one output at a time.
Yes, we can do that, right? So you take all x y1, build a model, all x y2, build a model, all x y3, build a model, right? When you have to make prediction, right, you need to pass x to all these models, model 1, model 2, model 3, model 4, model 5, model 6, and then form the output. All are binary class classifications only. Okay, so that is simple. There is nothing big there, right? Multi-label, they named it multi-label. That's it. Okay, it is a same input, but there are different outputs. That's it. Okay, so the realistic case, right? If you take a picture, like this is a picture. There is a bike, right? And there is a man, right? There is a cat, right? So there are 3 objects there. When I pass this picture to a model, ML model, right, it should be letting me know whether there is a human being present or not, bike present or not, right, cat present or not. Right? In every picture, you may not have all 3 objects, right? Got it, Grigar?
Yes, sir. It's clear.
Right? So you need to pass this model, this record to first model, second model, third model. Each model, if all models give you 1, 1, 1, that means all three objects are present. If it gives 0 on the second, human being is not there, bike is there, and cat is there. But if the 0, 0, 1, cat is there, all zeros, no object at all. Okay. On the object we trained is not present in the picture. There may be other images like trees and rocks and maybe elephants and tigers, but the objects we trained on are not present. Okay, that's the case. That's a real world case. Okay, so I took object detection or the computer vision example because in computer vision we'll be using these multi label and multi uh, output classifications. So if you are clear till this part, right, I'll explain multi output also briefly. Can I? Okay. So in the multi label, right, we had 0 or 1 here. If we have multi-class here, right, instead of 0 or 1, we have 0, 5, 9, like multiple, more than 2 classes in each of these y variables. Then we call it as multi-output classification. There are multiple y values, y variables. In each y variable, you have multiple labels, more than 2 labels. Then you call it as multi-output classification. We'll see one example of multi-output also. I'll show you an example which is very useful, but no, it's a bit confusing. Not a big deal, but a bit confusing. I'll explain you the use case also and then explain it. Okay. So here to do multi-label, KNN algorithm can do it directly. No, Seshiram said that you need to take x and y1, xy2, xy3, xy4 and build 6 models. Right? If it is logistic regression, we have to do it like that. But KNN algorithm can by default do multi-label classification. If you look at the API of the algorithms, right, they'll show you which algorithms can do, which algorithms cannot do multi-label and multi-output classification. So I have taken emotions dataset where we have many inputs, right, and there are outputs, right. Outputs are like this: amazing, surprised, happy, pleasant, relaxed, calm. This is about music. Okay, these are all digitized music. Somebody played an violin or somebody played drums. That whole data is digitized, converted into numbers. And then the target variable is flagged by human beings saying that, is it amazing? Is it happy, relaxing, or relaxing, calm, or quite still, sad, lonely, angry, aggressive, right? In movies, right, there will be different kinds of music, right? Generally, if there is a horror kind of music, right, I'll not watch, right? So like that, by music itself you can sense it, right? What's going to happen, or what might be happening, right? So like that, people, the guy who have actually created this data set, that guy took it and flagged the labels. So this is the data I looked into head. So if you see this, right, 1, 2, 3, 4, 5 and 6 are the target variables. So I have taken all those target variable columns into y, right, all rows from -6 till end. Okay, from -6 till end. That means 6 columns I will get into y. Rest all I am getting into x. Okay, so this is all x emotions. Right? This is all input data, right? Digitized music data. And then I have taken y and trying to look at it. See this? The first record is actually happy, pleasant, and relaxing, calm. The second record music is about surprised and aggressive, right? Third is about happy, pleasant, and aggressive, right? Happy, pleasant, and aggressive may be a war, right? Maybe a war and winning a war or a game. Right. So you got the data, how the data is that data is being found. Any questions there? Okay, good. So I am splitting data. The train test split again. It takes emotions, the input and y. Here the stratifying columns are multiple. Okay. So it is going to take happy, pleasant, and relaxing, calm. Right? Maybe 10 records are there belonging to these two categories. Then it will take one record into test set and 9 into train set. Okay. But this data is very small. This data set is very small. Only 593 records. Okay, it will not cover all the scenarios there on the train set and test set. We'll see that problem also in a moment. Okay. So I have taken the standard scaling and scaled it. Why? K nearest neighbors works well when you do standard scaling. Okay. So I scaled it, and then default, right, when I built the first time, I took n neighbors is equal to 3. When I say n neighbors is equal to 3 and say fit, right, it is not going to do anything. It is going to take this data and put it into memory. That's it. Okay. K nearest neighbors and then n neighbors is equal to 3, and fit, it's going to take this data and put it into memory. Now if I ask predict, it is going to take the first record and calculate the distance between all the 596 records, and then take the closest 3 and look at the target variable and make prediction. Got it, right? When you ask for prediction, that's where this Euclidean distance calculation and then the looking at 3 records and making prediction will happen. Y cap is going to be calculated here. Okay, metrics are same. F1 score, I've got 81% on the train set with the neighbors is equal to 3. Right? But is that the right right neighbors? Okay, that we need to decide. So to decide that, it's a trial and error again. Okay, so I have taken a range from 3 to 21. Step 2 I have taken. Why? Because if you look at this range method, right, it is taking 3, 5, 7, 9, like that, odd numbers only. But 21 it's not going to take. And then we are now in a loop. We are building the k nearest neighbors with 3, with 4, sorry, with 5, with 7, with 9, like that. And then I am doing cross-val score. What cross-val score will do?
Cross-val score is nothing but like cross validation. It's a K folder, right?
K-fold cross-validation. I'm just checking whether you remember it or not. Okay, you guys know it, but so it is going to make the data set into the train set itself into 10 pieces, and take the 9 pieces and put it in memory, and then use the 10th piece and try to make predictions like that. 10 times it will actually predict and try to take the average scores. Okay, I took mean of the scores, right, F1 score, and I took 1 minus, right. Generally F1 score gives you accuracy. Okay, and I am looking at error. Now opposite to accuracy is the error. Got it? 1 minus accuracy is the error. Did you get that point? I did. I said MSC. No, it should not be. It's not MSC. It is. Yeah, the name is wrong. So misclassification error. This is. Okay, misclassification error it is, right? You got this point, I think, right? I have, when you use cross-val score, it gives you 10 scores, right? And then all the scores I am actually taking mean of it and subtracting it from 1 to get the error, and I'm appending that to misclassification error and appending k also, so that I can do at what k how much misclassification error came. So with the number of k growing, right, the error is reducing. With 3, we have got no huge error. With 5, it reduced a little bit. with 7 it reduced even more, with 9 it reduced more, but with 11 it is raising again. Okay, 9 must be the best one. So I chose K. This is called as elbow curve. You know, it looks like elbow, right? Maybe a twisted elbow a little bit, but it looks like elbow. It is called as elbow curve. We'll do elbow curve like this. Okay, we'll take a for loop and choose different K, build a model and then do k-fold cross validation to make sure that the model works well on the test set also. Calculate the misclassification error, append it, right, the misclassification error in different case, append them to the lists and take those lists and do a curve. Okay, that is elbow curve. Wherever that elbow is cutting like this, you will take data as the best K. Now, for fun, I have taken 3 here, but by default, you should be doing this and then choosing the K and then testing it on the train set and test set. Now you look at train set, I got 72% and the test set I have got 63%. Okay, still the model is overfitted, right? Here, right? Why model is overfitting? How can we know? Oh, okay, I have 2 questions. So here with the 3, right, I have got 82, right? 82% accuracy. Sorry, 81% accuracy. But with 9, the accuracy reduced. Is that okay? Is that okay?
I think yes.
Why?
Because it is checking more number of neighbor records.
If we had taken this 3 as the neighbors, what would have happened? Any problem? If we have taken neighbors as 3, what would have happened? By looking at this, you can tell what would have happened.
I think overfitting will happen.
Overfitting would have happened here, right? Yes. It would have given 81% on the train set, but on the test set, it would have given 40% only. Test that, okay? Take this data and try to test it on test set and see what's happening, okay? The second question, right? Second question I asked is, I've got, still even after finding the best K, still the model is overfitting, right? How can you know, how will you analyze why this overfitting is happening and where the problem is? Where can be the problem? First question is, where can be the problem? Why that overfitting is happening?
Between train set and test set may not be appropriate. One possible reason.
Yes, sir. Yes, sir. Data may not be sufficient. When data is sufficient, the distribution on train set and test set would have been similar. Okay, that's one thing. The other thing, whenever model is not working, there will be 2 problems. There might be 2 problems. One with the data, another with the algorithm. Right? Algorithm would not have able to understood it properly. Right? So how will you know where the problem is? Do we have any tool, a technique to know where the problem is?
Learning curve.
Yes.
Learning curve.
Yeah. I would recommend you to do learning curve on this data set and test it on the test set and see where the problem is. Okay. So maybe tomorrow or Monday, one of you should be showing that. Okay. So in previous whatever notes, right, I had it in the notes itself, but people are not getting it. If you try it, you will get it. Okay. So where the problem is, why this overfitting is happening? Is this because of algorithm or data? I need an answer. Okay. So that is how you choose K. Okay. You know how to choose K now, right? So value of K will affect decision boundary in KNN. Okay. Smaller K, noisy decision boundary. With minor changes in the train set, the decision boundary will change. Okay, smaller K if you take, it is all dependent on train set, right? While predicting, it is actually looking into the train set. So if you take small K, you are looking into only three neighbors only. I'm taking only odd numbers 3, 5, 7 because when you are trying to calculate probability, right? It's going to be easy for the algorithm, right? Either two are going to fall into one side and one is going to fall to other side, right? So the decision making is going to become easy. So I'm taking k an odd number. That is one thing. If you choose a small k, when you add data or delete data in the train set, the predictions will change. The decision boundary will oscillate, right, with the change in data. Change in data is quite common in real time, right? Every day you'll get data, right? So that's higher k. With higher k, the model works consistently on train set and test set, but model may become underfitted. Right? If you see this here, the example actually shows you. When I took k is equal to 3, I've got higher accuracy, but when I took k is equal to 9, accuracy reduced. Right? The same point, trying to explain. When k is higher, the model may become underfitted. Underfitted means, on train set itself, it's not going to work well, but test set also similar. Right? So in real time, I never used KNN, but in interviews, people will ask because they know only that or only those algorithms, right? But there are many techniques we have understood here, scaling and and then the distance measures. If one of the columns values are high, how they are affecting the distance metric and all. This is important. This analogy, right, that whatever the theory, right, it's very important. For that purpose, I am explaining KNN. Rather, I would have avoided this. Okay. So one needs to trial and error to find out the best K. Right. This is trial and error only. Now I am putting it in a blunt terminology. I am not saying hyperparameter tuning and all fancy words here. It's a trial and error. So we are taking K3, 5, 7 like that and see where exactly the K-fold cross validation actually tries to see on the train set and the cross validation set the how model is working. If the model is working good on train and cross validation, most probably it will work well on the test set also. That's how we actually chose K. Okay, any questions?
So in this case also we can say that actual terminology is as hyperparameter tuning.
Yeah, we can say K, we are trying to tune, right? So when there are coefficients in the equation, we call them as parameters. When there are no parameters in the function or the algorithm, we call them as hyperparameters. So we are tuning the K, so we can call it as hyperparameter. Okay. So the next thing is there are algorithms that actually make the search faster. Okay. So here the KNN algorithm, what is it doing? It is actually calculating the distance between the new record and the existing, train records. Right? So this is taking this record and trying to calculate distances between all 10. Suppose that there are 10 million records here, and there are 1,000 records in the production, right? In the test set, you need to predict it. It's going to be 1,000 into 10 million. It's going to be too many calculations. Try to apply the KNN algorithm on the digit recognizer data set and see what's happening. Okay, that's another observation we have to do. Apply KNN algorithm on digit recognizer and come back and let me know what's happening there. Okay, so it takes a lot of time in calculating, so we can reduce that time. How can we reduce? There are two algorithms. Okay, three algorithms basically. Brute force is what we have discussed so far. It blindly calculates. It takes the data, it takes the record and blindly calculates distances between all the records and takes the k nearest whatever. The brute force computation of distance between all pairs of points in the data set. With the number of samples grows, the brute force approach quite quickly becomes infeasible. Okay. So in KNN, which algorithm is used by default? Let us see. So algorithm is auto. Auto means attempt to decide the most appropriate algorithm based on the values passed to fit. So it actually tries to find out which algorithm is actually best. Okay. So brute force is what I explained so far. KD tree, right? To address the computational inefficiency of the brute force algorithm, a variant of tree-based data structure has been invented. In general, these structures attempt to reduce the required number of distance calculations by efficiently encoding aggregate distance information of for the sample. The basic idea is if A and B are far and B and C are close, A and C are going to be far. So the KD tree will try to build a tree of records with closest distances, right? By looking at the tree, you can say whether A and whether a record is close to another record or not. And a new record came in, you calculated the distance between C and B, right? C is the new record. Suppose that C is the new record. You already have A and B. You know that A and B are far, and you calculate distance between B and C. Definitely, the C is going to be far from B, sorry, A, right? Because B is already far from A, definitely C is going to be far from A. No need to calculate distance between C and A. That way you are reducing calculations, right? Got it?
Yeah, there is possibility that it depends on the how much close or how much far, sir.
If data is too huge, right? And it depends, but but you can actually go in a direction where you will be connecting to only closest records.
Sure.
This may be far, but you take another record, maybe D. It is also maybe far, but it may be closer than A, right? B and A are too far when compared to B and D. Then you can actually take distance between C and D, because anyway you have to choose 3 neighbors or 5 neighbors, right? So the direction will be set appropriately.
Yes.
Well, definitely some reduction will be there in distance calculations. You no need to calculate distance between given record and all records. You have to randomly pick some records and calculate distances. Then you will know, right, whether it is close to some of the records or not. Then depending on the closest records, you try to take other information and decide on whether to calculate distance with the other record or not. Randomly pick some, calculate distance like this, take the closest, and then try to take the record and that closest to that record, and then like that it's going to go. Closest to closest only it's going to go. Because it's already having a tree structure in the memory. Okay, and that's KD tree. Okay. And there is another algorithm called as ball tree. This is a bit confusing, right? I'll get confused whenever I come here. A ball tree recursively divides the data into nodes defined by a centroid C and radius R. Okay, it takes a centroid C and a radius R. It tries to consider one data point, right? Some A or B as a centroid, and then it takes a distance measure R and tries to form a group there, right? It's like the data points falling in that radius are going to be closest to C, such that each point in the node lies within the hypersphere defined by R and C. It's a if it's a 3-dimensional one, right? It's going to be globe. But if it's 4-dimensional, I don't know how it's going to be. So 3 dimensions means if you have 3 input values. 3 input values is going to be globe, right? With the R radius and C as the data point. The number of candidate points for a neighbor search is reduced through use of triangular inequality. Okay. Mod of x plus y should be less than or equal to mod x plus mod y. That's how. Now this is the formula where it tries to decide whether the x and y are close to each other or not. Okay. Within with this setup, a single distance calculation between a test point and the centroid is sufficient. Right? Whenever you get a data point, right, you take all the centroids and try to calculate the distance between the new data point and centroids to determine lower and upper bounds of the distance to all points within the node, within that cluster, or within that what you call it as the hypersphere. Okay. Because of the spherical geometry of the ball tree nodes, it can outperform KD tree in high dimensions. Though the actual performance is highly dependent on the structure of the training data. Okay, that's another constraint. But basically, in a high dimensional space, I never prefer KNN. If you are using KNN, it is better to use ball tree algorithm. So this based on it actually form hyperspheres and then take the centroids and calculate the distance between the data point and the centroids, find out the closest centroids, and then take the the neighbors from those whatever centroids. Okay, got it?
X and Y is not clear to me, sir. X and Y.
Yeah, X is the the record we are trying to predict now, and Y is the centroid, right?
No,
Centroid.
I think they're talking about some distance kind of thing, right?
Yeah, distance measure only. X plus Y is like um, okay. If I say distance, there should be 2 points, right? So X and Y. Yeah, X is going to be the distance between um, one centroid and the data point. Let me think. One centroid and data point and another centroid and data point. Y, right? Then if you take either Manhattan or the Euclidean, right? You are going to get positive value only. There is no need to take mod there. So
What I'm visualizing is X. Let's consider X is a distance between, let's say, 2 points, two neighbors, and Y is the distance between, let's say, X is the distance between A and B, and Y is the distance between, let's say, B and C. Just assume. This is my understanding, sir.
yes, sir. Yes, sir.
In that case, between A and C, they are trying to conclude, saying that in a triangle kind of thing, because X plus Y, that is distance between AC, is always less than AB and BC. That's how they're trying to use this particular
Let us write
approach.
it down. Let us write it down and try to understand. I think that's. I think here, right? They are not taking Euclidean distance. They are taking normal distance, right? So it's like not a mod, right? You take 5, 6. Let me take a data set here. X1, X2. Right? Why we are not bothered about it? Let us take 5, 6, 8, 9, 3, 2, 5, 4. Maybe some data, right? Let us take X as distance between this record and this record. Okay? So 5 minus 8 plus, I'm not taking squares because they are considering mod here. That means we should get some negatives also, right? So, oh, no. So we are trying to calculate, right? We are trying to find out this data point, distance between this data point and other data points. Let me try to calculate that. This is A, this is B, and this is C. So we are calculating bit distance x, we are calling it as bit distance between A and C. Okay. So A and C can be calculated like, first I'll take A, right, 5 minus 5 plus 6 minus 4. Okay, that's going to be plus 2. Okay. And Y, I'll say distance between B and C. Okay. Now I'll take 8 minus 5 plus 9 minus 4. Both I got positive. Right. So 3, 5, 8, right? Sorry. Uh, 3 and 5, 8. So I have got, so if I get negative value, then I would have got like, maybe I'll put 2 here. Maybe I'll put 4 here. So 4 minus 5 and 2 minus 4. That's going to be minus 1, minus 2, minus 3. Okay. So mod of x plus y is going to be 2 minus 3 less than or equal to mod x is 2, mod y is 3. Right? This is 1 less than or equal to 5. So what that means? This is satisfying it. X and y are satisfying it. That means what? They are close. The number of candidate points for the neighbor search is reduced through the use of triangle inequality. Basically, I forgot what this is. What this triangle inequality is, I forgot.
Yeah, triangle inequality is nothing but in a triangle, distance between, let's say, two sides, sum of two sides, length of two sides is always greater than the third side, sir. That's the triangle inequality.
Okay, okay. So if the data points are like this, we'll say that these two are neighbors, right? What we did is we calculate distance between this and this and this and this.
Yeah.
Right? This and this is x, this and this is y, right? Then x plus y, mod x plus y must be less than or equal to, it is always going to be like this, right?
That is correct, sir.
It is always going to be like this. So that is this rule. Okay. So we have got that also, right? When we did the previous thing, right? 8 and 9, what happened? 8 and 9, 8 minus 5 and 9 minus 3, it actually 8. So it's going to be 2 plus 8 less than or equal to, okay, 2 plus 8. Okay, it is always satisfying this condition. The point here is, right, triangle inequality is going to be there. The data point is going to look at the distance between the centroid, and then choose the set of values, and only in that spherical hypersphere it is going to choose the data points and then calculate the distances. The distance calculation space it is reducing by using hyperspherical whatever. The number of candidate points of the neighbor set is reduced through use of, yeah, I think it is simple. I think it is going to take the data point, the record we want to predict, and take the centroids and calculate the distances x's and y's, right? There will be many x's, or there will be many values x, y, z, like that, right? And it is going to this rule is going to satisfy there, and it's going to choose the closest one, kind of, right? If we have many centroids like these, right, there will be, every time there will be a triangle inequality, right? So if you take this x and try to calculate distance between this and this and this and this, right, there will be triangle there also. Like that, some kind of concept, right? Got it? We need clarity there. Maybe, give me some time. Maybe tomorrow I'll explain what this is. Okay. I think vaguely we understand, right? Yes, no?
Yes, sir. Yeah, at least my understanding is it tries to visualize or make a visualization of all the data points into a tree with nodes all around some center kind of thing. So
Yeah.
like a circle or sphere.
No, there will be circles. There will be balls. Right?
Yeah.
There will be many balls. It is going to take the data and it's going to make many balls out of it, right? Each ball will have some set of values inside it, some data points inside it, and when you pass a new record, right, it's going to calculate distance between the centroids of the balls and which centroid meets the closest distance condition. It is going to take the data points from there and calculate distances and find out the closest ones. That is, in a simple terminology, ball tree works like that. Okay.
Issues.
Let us look at that API. Maybe we'll get some idea there. Yeah, here it is. I got it from here only. Okay. Ball tree data structure was developed the KD tree data. The ball tree recursively divides data into nodes defined by centroid C and radius R such that each point in the node lies within the hypersphere of the R. The number of candidate points for neighbors H is reduced to use of triangle inequality. The number of candidate points for neighbors H is reduced. I didn't get this point, I think. We'll see. Now I'll look into this and then come back tomorrow. Okay. So let's move on. So let us look at this multi-output classification. Okay, multi-label classification we have seen, and now multi-output classification. So where we'll get this kind of a problem, right? That's a real time where we'll get this kind of a problem. Suppose that there is a document, scanned document that is blur. Okay, we need to unblur that. Okay, or in a speed detection system, we take the pictures of cars and number plates. Okay, the number plates sometimes come blurry because the vehicle is going very fast. The camera may not be able to capture the picture, right? So we have to unblur that car number. To do that, what we have to do is either a document or a number plate. Right? This is a document which is blurred. We have to make it unblur. Right? So when you have to make this blurry document unblur, right? We have to have data that is actually resembling the same thing, right? So you can convert this document, right? This is a image into pixels, right? You can convert this image into pixels, and you can convert the clean image also into pixels. So first thing is that you already have a blur document, you have to do it as into neat one. So what we will do is we'll take neat documents, maybe 10 documents we'll take neatly, neat documents, and then add some noise. Okay? Add some noise in such a way that these neat documents become like this. Okay, now we'll have blur documents. Okay, we prepared a data set. Okay, now what we will do is we'll take these blur documents and convert them to pixels. Take these neat documents, convert them to pixels. We will use this blur document as input. Right, the blur document is input and neat document is output, and build a model. Okay, now the algorithm, the model knows how to convert, how to find the neat document by taking the blur document. Right, so now you pass your blur document, you will get neat document. That's how you build it. Got it? Got the problem statement and data set formation and then building model. Any questions?
How is it a multi-label?
Sorry.
How is it a multi-label?
How is it? I didn't get, sir.
Multi-label. We are actually trying to.
Yeah, multi-label only, because if you convert a document into pixels, you will have, suppose that it's a number, handwritten digit, 784 pixels here, right? Right, original document, neatly written number 2. Blur 2 will also have 784 pixels, right? Each pixel will have a value between 0 and 255, right? Got it? In the input, you will have 784 pixels. In the output, also 784 pixels. Each pixel will have a value between 0 and 255. So you are predicting, right? You take this data and predict the first number, this data second number, this data third number, like the 255 number, 256 numbers you will predict, 0 to 255. Got it? In each cell, you are going to predict one number out of 0 to 255.
So the bit number changes from input to output. So it's actually pixels only, right?
Pixels only.
84 pixels.
No, we will go into that detail in a moment. I think I may be confusing you a little bit. Did you get this problem and the solution?
That I understand.
This part you understood, right? I'll explain that next part. Why, how it becomes a multi-label, I'll explain. Sorry, multi-output, I'll explain in a moment. Right? This is a real problem in the industry. There is a real problem in the industry. But while you are taking the neat documents and trying to blur, you should see the data distribution, how the blurry documents in the company, the data distribution you need to understand and try to replicate that data distribution in the blurry document and then build a model, between the blur document and the original document. It is like this. You have number plates, right, collected from the cars, and there are 1,000 number plates which are neat. You take those number plates and try to make them blurry by looking at the blurred number plates and data distribution in those blurred number plates, and then build a model. That is called as deblurring. Sometimes we can use a GAN, generative adversarial network. That's a deep learning technique which actually tries to generate synthetic data by using existing data. Okay, so you can take blur documents and then use GAN to generate those many blur documents. Okay, so like the Maybe you can build a model to take the original and the generate blur like that. GAN is useful there. Okay, so generating data also we have tools in AI deep learning. Okay, so let us try to take this example, right? Digit recognizer data set, and I'm going to create some synthetic data here. See this? I generated some noise, okay? And then I'm adding noise to the original data. Okay, so this is going to be input now, right? This is blurry numbers I have. Okay, I have original numbers also. In blurry number also I have 784 pixels, and each cell has got a number between 0 and 255. And the original picture also I have 784 pixels. Each cell has got a number between 0 and 255. Right? Input has got 784 pixels, output has got 784 pixels. Now there is x1 to x784 in the input. There are y1 to y784. In our previous example, right, we had only 6 y's, y1 to y6. But in this particular example, we have 784 y's because we are trying to generate the same picture. Okay. In some other case, right, you may have less number of y's also. Maybe 10 y's are there, but each y is having more than 2 classes. Here, this picture has got a cell 784 pixels, and each pixel will have a number between 0 to 255. By taking this data, you need to predict in each cell a class more than 2 classes. Right? It's not just 0 or 1. You need to predict a number between 0 and 255. Got it? That became a multi-output classification. Got it?
Yes, sir. It's both multi-label and multi-output, right?
Multi-output only. In each cell, you are predicting more than 2 classes. One of the numbers. Huh?
The overall conversion to neat document to blurry.
Neat document to blurry, we just added noise. That's it. See this, I generated noise and added noise. That's it. I converted neat document to blurry. That's it. This became blurry.
No,
This is data generation. This is data set preparation. Okay. Now we are passing blurry document and generating neat document. If you get a in production, right, if you get a blurry document, you can pass that to the model and it will generate neat document. Getting it is a bit confusing. That's it. There's nothing big there. Got it?
Are we trying to do some reverse engineering kind of thing, sir?
Yeah, reverse engineering only. Reverse engineering only. We have some blur documents. We actually have to make them neat, but we don't have corresponding neat documents for the blur documents which are existing right now. So what we are doing is we are taking some neat documents and trying to corrupt them in such a way that they actually resemble the existing blur document. Right? That is dataset preparation. Till that far it is dataset preparation. Right? So I took a neat document and added noise and created blur document. Right? So I have blur document and corresponding neat document. This is blur document, corresponding neat document. So I can pass this as X, this as Y, and build a model which actually be useful to unblur the existing documents. Got it?
Yes.
So actually we can do a project, right? In this area, if we can find some, some data, maybe over the internet, if anybody, if you guys have time, if you can find out a data set there, and I was actually looking to do a POC on this. If we start doing POC here, right, till deep learning will have a work in this. Right, in GAN we can generate lots of data and then try to build a model and all that. With deep learning also we can solve the same problem. Got it? Now you are looking for projects, right? This is one project I was looking to do for a long time. We need data. Got it? Anybody? Can anybody help finding data? Guys?
So you mean some blurred images kind of thing?
We need neat images. Even if we have neat images, that's enough, right? We can actually blur them, and then or if you have blurred image and neat images, and we actually have to understand the data distribution and try to blur the original images into that kind of blur. To start with, we have neat images, neat documents somewhere. The OCR stuff, right? So we need to have GIF files or the PNG files of the document, not PDFs. Can we get some from somewhere?
Yeah, we'll try to I'll try to explore and see if I can
Please,
at
please.
least some images.
Yeah, please do. Everybody, Narayana, Seshiram, Prudvi, did everybody try to come up with a data set? Srinivas Gar, I think you have time, right? You also spend some time and find a data set. We'll build a use case. We'll build a POC actually.
Yes, sir. Okay.
It is just the beginning. Here in the machine learning, we'll start it. We may not be able to produce good result here, but by the time we end the course, right, we'll be able to produce a very good result on the data set. We should be able to produce it. Okay. So please work on this, right? This is going to be our project for this batch. Okay. So here the min-max scalar I have taken and then transformed the noisy data. This is the input, right? Blur image is the input, right? And then I'm building a model here, right? Blurred image I am passing, no noise, the original data, right? Clean image as the output I am passing, because the ultimate goal is to pass the blur image and produce the neat image, right? So I am generating, I built a model here. KNN can handle multi-class and multi-output both. And now I've taken one record and did min-max scaling and predicted, I took that blur image and passed it to the model and predicted, see this, it unblurred. It is not as good as the original image, but it is almost, right? All that noise got eliminated. Because it's the synthetic data, it is working better. But if you take a real data, right, real data, a blur document which is already existing, you keep that aside, you take the neat documents and try to reproduce or try to produce the data distribution as the blur image we have and try to build a model, it may not come this neat. Okay, that's the struggle we need to do, right? That's where we need to spend a lot of time and make. This is a huge problem in banking and insurance and all the industries, those kinds of industries. Okay. So I'll stop here, and I think next topic is going to be SVM, support vector machine, and that I'll look into this. This thing. I think this point I highlighted also. I understood and highlighted, but I forgot. Somehow I lost the link. The number of candidate points for the neighbor search is reduced through use of triangle inequality. Okay. Okay. So x and y and x and z. Let me attempt a small thing here. We have time, right? So suppose that distance between this and this is x. Distance between this and this is y. Distance between this and this is z. Okay. So now x plus z must be less than or equal to x plus y. First, I need to look into triangle inequality. Then I'll understand what this is. And as Girigar said, right, it may be that. But if you take equal, that equal length will be there, right, in a triangle. Then it's going to be equal, right? So, and there will be three, right? Three distances, right, in triangle. Why the way took x and y?
That is about the third distance, sir. Third distance, what they are saying is it has to be either less than or equal to the other two distances. That is the rule.
Aha, this distance is z, they are saying.
Yeah, yes.
This is z.
Yeah, it's about z, yes.
Okay, okay. But it is not going to be x plus y, right? Always in triangle.
No, they are saying actually it is actually x plus y is less than x plus x x and y. When I say x plus y, the z that is always less than x plus y. Sir.
My problem here is, right, the way I understood before was there are three centroids. This is one centroid, right? That is another centroid. That is another centroid. There are data points around it. Okay. Right. Or no, let us take. Give me 1 second. Let us take this as a new record. Right? Let us take this as a new record. And there are two centroids. Okay, now I think I am getting clarity. Give me 1 second. Now I am getting clarity, I think. Right? This is a data point. Right? This is x. This is y. Okay. So there is another. Right? Let me take another. The same data point, a blue dot. Right? There is another centroid. There are two more centroids. Two more centroids like this and like that. Okay. And there are data points around it. Right? Now this is also, this is A and B. We call that as A and B. Okay. Now I need to say x plus y less than or equal to mod x plus mod y. So I am trying to choose, one centroid, right? One centroid which is close. How this equation is helping? That's my, as that's your question basically, right? Right. So how is it actually deciding on which to take, right? I don't know. Maybe this thought process is not right. Greer, do you think this is right?
Yeah.
We are trying to choose one centroid. Maybe this is close, or this is close, and then take the data points inside it, and then calculate distance between this dot and those data points, and then find out the nearest neighbors and make a prediction. Instead of looking into all data, we are looking into only the spherical which is close to the data point. But this equation, how is it actually deciding? That's what your question is. And I am also got stuck with that.
Yeah. So at least my understanding, sir, x is nothing but let's say if I take let's say 2 points, x is the x-axis distance. Let's consider x-axis distance, and y is the y-axis distance. Then that is between, let's say, if you can denote points as A, B, C. So the x-axis distance between A and y-axis distance or maybe between A and B, x-axis distance and y-axis distance. If you
no, sir. No, I think because if you have only two input variables, right, then x and y. But if you have 10 input variables, there will be more, right?
No, I think here the X and Y are not about input and output, sir.
I think, right, there is one more point we need to understand here. The candidate points for neighbor search, right? Candidate points for neighbor search may be within the spherical. Inside the spherical, right? Inside that spherical, 2 data points and your data point. This is X, this is Y, and maybe another data point. This is Z. Right? X plus Y. X plus than equal to X plus Y. Oh, I got it. Right? So let me explain this. I think I got it. Give me 1 second. So this is your data point. Right? Suppose that you zeroed on this particular spherical. Okay? And inside that spherical, you have got maybe 3 data points. Okay? You wanted to see which one is close out of these, maybe 5 data points, which 3 are close you want to find. Now you need to calculate distance between this one and this one, say X, this one and this one, say Y, right? This distance is not the Euclidean distance kind of formula, right? So you have right, maybe this one and this one Y, I will say this is negative value, this is positive value, this is positive, this is negative, right? This is positive, like that, right? So you take the X and Y, right? It is 3 minus 2 less than or equal to, right, 3 plus 2, right? It's going to be less than only 1, right? And then the other, maybe this is 5, right? 3 plus 5 less than or equal to 8. 8 less than or equal to 8. No, still having confusion. I'll look into this. I'll look into this now and explain you tomorrow. Okay? Leave it. So it's all getting